Okay, so I think we'll postpone for a few minutes questions about the homework. I want to show you how to show you something that might help with the homework. Anyway, at the end of class last time we were talking about, there's actually this one crucial slide. This one, figure 10.12. Remember what we said last time is that, and we have to always keep this in mind, for every Boolean expression there is exactly one logic diagram, and for every logic diagram there is exactly one Boolean expression. So there's a one-to-one correspondence between these. But a truth table is more general. One truth table can have many different Boolean expressions with its corresponding logic diagram. Are you with me? So that we have we just always have to keep that one in mind. Now, at the end of class last time, we were seeing what the correspondence was between a Boolean expression and a logic diagram for which there is a one-to-one correspondence. And we looked at figure 10.14, and we saw how you could construct this circuit that represents the Boolean expression A and B or B and C prime, quantity ANDed with A, and then the whole thing inverted, right? And then we said that there's two kind of ways to abbreviate this. First of all, for every variable, it's easy just to slap in an inverter and get its complement for every input variable. And also, if we have an input value that is the input to more than one gate, it's easy to take a wire and just to tap the signal off of that wire and have it be the input of another gate. So it's not like current. This is the difference between current and voltage, if you know anything about electronics. Because like if you have a river and there's a fork in the river, and then so like if a river's going downhill and there's a fork, and there's a stream, it forks off and the stream goes one way, another stream goes the other way. The amount of water that flows in each one, if it's evenly divided, half the water would go here and half the water would go there. Are you with me? But that's not the way this works. It's not like the signal coming in from A, half of it goes into that first AND gate and the other half of it, it's not like half the signal goes. The whole signal goes. It's more like pressure. It's more like pressure it's more like these are pipes, and the water that's flowing, it's not like half the water flows. It's like the pressure stays the same in both. Do you see kind of physically what that analogy is like? So you can always tap off. And so we said as a result of that electrical characteristic of circuits that we can always do that. Then we frequently don't want to have to mess with all those taps and the inverters and all that kind of stuff. So we can abbreviate it as in figure 10.15. And we can just put A here, and then if A is the input of another, we just draw a little short wire there and put A there. But really, physically on the circuit board, there is a wire going, that's tapping off of that one. Does everybody see how that works? And then inverters, we can have a NAND gate instead of a AND gate followed by an inverter, and so on. And here also, even with the input, instead of saying if we want to have C in the if we want to have not C, C prime going to the input of a gate, we'll just label it C prime. And what that means is C is coming in from the left. Well, there's really an inverter there, but we just abbreviate it by not showing the inverter. Is everybody clear? And here is an example, figure 10.16, of a circuit diagram that shows that Boolean expression. A prime and B and C, XOR C. Now what was the, and then OR A or D, and then the whole thing inverted. Now what was the precedence between AND, XOR, and OR?
XOR, or
XOR was what?
First.
Was it?
And.
No, it's in between, isn't it?
Yeah.
XOR was in between AND and OR. So does everybody understand that what this means is A prime and B and C first. So that's coming into that left gate. And then we XOR that with C. So there's an XOR gate, exclusive OR gate, right? And so C's, and really, this is an abbreviation, so there would be a little tap going into there, right? Okay, and then, and this, here's an, and here's an A prime, so really there's an inverter there, and you'd tap in this before the inverter on that one. Does everybody see how that, are you with me on this? Okay, and then there's A and D, and then the whole thing is inverted, so we just make a NOR instead of a OR followed by an inverter. Is everybody good? Okay, so now, so that's how these circuits work. Now, here is, and I think this was one of the things you had to do. Given a truth table, it's always easy to write a Boolean algebraic expression that represents that truth table. But remember, this recipe is just going to give us one of many possible Boolean algebraic expressions. Are you with me on this? You have to keep that in mind. So let's take a look at how to do this. Here's the recipe. Given a truth table, you write, it's easy to write a Boolean expression without parentheses as an OR of several AND terms. Now, let's illustrate this by going back. Here's figure 10.3, and here we have a 3 input, 2 output truth table. And so, and what we want to do is we want to write a Boolean algebraic expression for x. So here so x equals what? How can we write down a Boolean algebraic expression for x that matches this truth table? Well, it's pretty easy, because look, where is x 1?
When C is 1?
Not necessarily.
When C is 1 and A is not.
Well, what are the combinations that will give x equals 1? What are the combinations? What combinations of A, B, C will give us x?
0, 0, 1, and 0, 1, 1.
Yes, 0, 0, 1 and 0, 1, 1. Are you with me? So look, 0, 0, 1, what we do is we'll do A prime and B prime and C. Because if A is 0, A prime is what?
1.
If B is 0, B prime is what?
1.
And if C is 1, well, C is 1. I mean, are you with me? So this is going to be 1. I mean, when ABC is 0, 0, 1, this will be 1. Are you with me? And then all you have to do is OR that with the other case where
A prime BC.
and because the combination is 0, 1, 1, that would be A prime B C. So do you see how to read that off the table? Or A prime B C. So now let's think about how the OR thing works. Does everybody agree that this is going to be 1 for just one of those 8 combinations? Otherwise, it's going to be what?
0.
0. Are you with me? And furthermore, this is going to be 1 for just one of those 8 combinations. Otherwise, it'll be what? It'll be 0. So when this is 1, this is going to be 0. And when this is 1, this is going to be 0. But the whole thing will be, so therefore the whole thing will be exactly 1 and only in exactly 2 places. So do you see how to do that? So it's important to be able to read off the combination from the truth table and to see how that matches this. Yeah.
Could it then be an exclusive OR and it wouldn't change anything?
Well, this recipe gives us one way to write it.
Right.
And that's all we're interested in right now.
Gotcha.
Okay, because we're going to see there's big implications on what's the best way to write it from an optimization perspective. And that's coming later. But just to keep that in mind, all right? So tell me, what would be, can you just, without writing it down, what would be the equation for y?
A prime BC.
A prime BC or
A prime C.
B prime C prime. Now, is everybody clear on that? Are we good? Okay. Let's do figure 10.4. So this was figure 10.3. Let's do figure 10.4. So now what would this one be? Let's do x.
A prime B, C prime D.
A prime B, C prime D, good. Or
A prime B, C D.
A prime B C D. Is there another one?
There's two more.
Yeah,
Or
ABC prime D.
A B C prime D, or now, do you guys agree? I'm not gonna. I hope this is right. Yeah. I'll take your word for it. And similarly for Y. Is everybody? Are you with me? Now, see. So this is, and so now, what we call this format we call. Do you understand? We call this an or of and terms. You see what I mean? We're going to call this, there's a more technical abbreviation. I don't want to use the jargon. There's jargon for this, but we're going to call this as an or of and terms. And do you see why we call it an or of ands? Because each one of these is an and then we have an or, and we don't have any parentheses. Are you with me on that? So given a truth table, we can write an expression, an or of and terms, just like this. Did you also have, was there also an exercise where you had to take a Boolean algebraic expression and convert it using algebra to an or of and terms? I think, was that one of your exercises? Or not?
Well, we didn't even have to do truth tables.
Oh, you didn't? What did you have to, okay, well, now's a good time.
Boolean to truth table.
Oh, Boolean to truth table. Oh, that's pretty easy, but do you have questions?
My question was on drawing an abbreviated logic.
Oh, your question is drawing an abbreviated. Okay, what's your question?
So I was wondering
Let me
if
get
you can use the, like, do we need to use the inverter? Or can we just draw the circle next to it? Like, I didn't know if we could use the NOR gates or not.
Yeah, sure. Yeah, you can use NOR
Because you
gates.
specified in the problem that you can use the XOR gates, but you never specified the other ones, so. I didn't know if it's.
Oh, I see. Yeah, no. Yeah. So the question was, is it okay to use NORs and NANDs? And the answer is yes.
Okay.
Yeah. That's what I had intended.
Okay.
Yeah.
Well, it's a lot.
Yeah, question?
Are the non-abbreviated versions going to be important, at least for doing the homework? I know they're going to be important in the labs, but would we do more problems like this?
Actually, what happens is, in the lab, that's the one time you don't use abbreviated diagrams.
Yeah.
Because in the lab, what you're doing is you're hooking up the wires.
Yeah.
And so with the lab, it's going to be really important. We will almost virtually never, I can think of a time when we'll use abbreviated diagrams in the lab. Because we're going to be working with circuit boards.
Yeah. Okay.
So, and the wire has to be connected to this and, and with the physical gates. So, but it's very common in design and analysis problems to use the abbreviated diagram. So it's the opposite. It's here we use the abbreviated, in the lab we won't. Okay, does everybody see how that, any more questions about the homework? All right, good deal. Now, there's another thing that we need to be able to do is that algebraically, it's important to be able to convert any Boolean algebraic expression to an and of or terms. All right, and it's always possible to do that. And actually, let's see. Let's get a concept here. So if we have let's call this. If this is a Boolean algebraic expression, let's say Boolean algebra to and of or. Boolean algebra to and. Oh, sorry. It's an or of and terms. Isn't that what we had last time?
Yeah.
It was an or. Yeah, I had it the other way. To or of and terms. Now, one way to do this is, if you have a Boolean algebraic expression, you could always do what you did for the homework. It's easy just by doing, each individual case, to go from Boolean algebra to a what? To a truth table. And then, using this technique that we just used, you can go from the truth table to a what? To an or of and terms.
Right.
See? But it's also, you should also be able to do this. You should also be able to go from Boolean algebra and do some algebra steps, do some theorems, you know? Do some theorems to get to an or of and. Do you see what we're saying here? So let's do a few of these just to see how that would work. Now, one thing that we have to do is that we have to understand what is exclusive or. Because if we want an or of ands and we have an exclusive or, we've got to get rid of the exclusive or operator. Do you see what I mean? So do you remember what this is? If we have A XOR B, do you remember how to write this as an or of and terms?
Not equivalent here.
What is this equal to as an or of and? What is exclusive or?
Or B prime.
Yes, good. It's A prime B or,
B prime.
actually, here's another thing, you guys. When we're doing these letters for the inputs, always just keep them in alphabetic order. If you start, it gets really confusing if you have, instead of saying A, in other words, don't do this, A prime B or B prime A. Don't do that. Do A prime B or A B prime. Keep these in alphabetic order. You see what I'm saying? Because if you start switching them around, it gets really confusing really fast. So keep these in alphabetic order when you have your and terms. Okay, so there's that one. Now, let's do an example. Suppose we have A XOR BC or AC. Let's focus over here. Suppose we have this expression. Suppose we have A XOR BC or AC. And the problem here is to write as or of and. Okay? So let's see if we can do this. So this equals by, now what's the first thing we should do? We have an XOR here, so how are we going to do this?
Well, use that fact.
Yeah, use that fact. And so do this by definition of XOR. That's a property, we could say property of XOR. So what would that be?
Prime BC.
So it would be A prime and what? BC or A.
And BC prime.
Yeah, but it's going to be A and it's going to be the quantity BC prime, is it not?
Yes.
And then what? Or what?
BC.
Or AC. Now, is everybody clear on this, on how that worked? Because this has higher precedence than the XOR, so we have to do the and. So this XOR, this primed is over the and. Are you with me? So, but now what is this? What is B and C prime? Because, we can't have any parentheses. Remember, we say without parentheses.
Oh, De Morgan's.
So, yeah, so now we got to do De Morgan's on it.
De Morgan's of and.
Okay, so now we do De Morgan. Does everybody see? Because we don't want any parentheses, yeah? So this would be what? This would be, and so now, sometimes here's an and here's an and, so we can just make this A prime BC. We can just not show the multiply or the and. And now this is going to be what? Or what?
A and
A and
B or C. prime
B prime
or C.
or
C prime.
C prime, right? Plus what?
AC.
AC.
Or
Or
Sorry, or AC. Okay, A and C. And now, but we still have our parentheses, so now what? This equals by what? Distributive, what distributes over what? And distributes over or. So distributivity of and over or. So that's going to be what? A prime, B, C, or what?
AB prime.
AB prime, or
AC prime.
AC prime, or
AC.
AC. And there we have it as an or of ands with no parentheses. Are you with me? Does everybody see how to do that? Now, how would you do this one? Figure. This is a kind of a long one. We won't take time to do it. But could you see how to do figure 10.16? What would you have to do?
Use the exclusive or.
Yeah, you do the exclusive or, and then that would be, what would that be? That would be A prime,
Well, it'd be quantity.
A prime BC.
It would be
Oh, it'd be quantity
A prime BC prime.
A prime BC prime
Prime C.
and C, or A prime BC
C prime.
and C prime. Maybe we should do this one. Because we would have a C and a C prime. Do you know what C and C prime is?
negation.
C and C prime is 1.
No, is it 1 or is it 0? C and C prime is 0, isn't it?
Yeah.
And then the 0
Diction.
and the other ones is 0, and then the or that would go away. Yeah? Yeah, 1 is true, 0 is false. Are we good? Is everybody clear on that? But now we have a not out of the whole thing. So what would we have to do? We want to get rid of the parentheses, so what would we have to do? De Morgan. And that would make it what? The prime of the first one and the prime of the second one and the prime of the third one. But the prime of the first one, there's more than one letter. So you'd have to do De Morgan. But you could do it.
Yeah.
It's 0.
You could do it. I think there might be an exercise to do this in the next.
Believe in us.
All right. Is everybody following on all this? How this all works? Okay. So here is the recipe. We did that, and here is now. Check this one out. Let's take a look at Figure 1017. Now watch this. How could you? Let's do our.
Or of n terms.
Yeah, let's do our or of and terms. Figure 1017. So let's do. So here's Figure 1017. Now, can we do this pretty quickly now? Because can you just read that off real quickly? So what would this be?
A prime.
X equals what?
A prime B prime C prime.
A prime B prime C prime,
A
or
prime B prime C.
B prime C,
Or
or
A prime B C prime.
or
A B prime C prime.
B prime C prime, or
A B prime C.
A B prime C,
Or ABC.
or ABC. Did anybody, everyone else check this? Is this right? Do we have a truth by democracy? If the majority thinks it's right, it is. Okay. Now, and furthermore, we could do the same thing with Figure 1018, right? What would it be? Let's just say this one.
A prime
B prime C prime D prime,
Or
A prime B C prime D prime, good, or A prime B C D prime. Yeah. Okay. Now here's the thing. Here's the thing. Here's why this is important. Why this particular format is important. It's because now let's go back and see. We keep going back and forth between circuits, Boolean algebra, truth tables. Now. And we've seen how to go from one of these to another. Now look here, you guys. Once you get it into an or of and terms, tell me, what would the circuit look like if I asked you to take your templates out and draw this circuit?
It would look different.
Well, can you tell me what it would look like? I mean, can you visualize what this would look like? What would it be? How many?
It would be
How many?
lots of.
How many gates? How many of what kind of gates? Ands, because look, this is an and of, no, sorry.
An or.
This is an or of and gates. My question is, you say it again?
6 AND gates joining to 1 OR.
Yes, there's 6 and gates. Are you with me? And how many or gates? 1. Now that is an example of a 2-level circuit. All right? That is an example of a 2-level circuit. I hesitate to draw gates on the board, you know, because I don't have a template. I need a big template. Anyway. And then these all go 1, 2, 3, 4, 5, and then this one big OR gate. You know, I don't want to draw anyway. But anyway, you can see that. But it's 2-level. And now here's what we mean by, here's why that's important. Now, nothing in the universe happens instantaneously. Right? I mean, even the sound waves that go from my vocal cords to your ears, you're not hearing me at the same time I'm saying it. And furthermore, you are not even seeing me at the same time. Because it takes a finite amount of time for the light to bounce off here to my face to here, or to the screen to you. So you are actually seeing me in the past. We all are. Yeah, and it takes a while for the brain to process it too. So who tells what the delay between that is? So no matter what, now when you look at the stars, you're looking at billions of years in the past. But the point is, nothing in the universe happens instantaneously. There's always something, events always span a certain amount of time. And it's the same way with circuits, the same way with electrical circuits. If you have a gate, here let's just, I will draw one OR gate here. Okay, so. All right, and here's the point. Suppose this is a 0 and a 1. What will be out here? 2. 1. 1, right? Because 0 or 1 is 1. Are you with me? Now, if at some instant in time I change this to a 0, this does not instantaneously change to 0. Because what's inside here? Some transistors. Are you with me? At a lower level of abstraction. And it takes a while for the signal to propagate through this gate. The amount of time it takes to propagate through this gate is called the gate delay. So sometime later, this will turn to 0, but only after a certain gate delay. Okay, so that's called gate delay. And the definition of the gate delay is the time it takes a change in the input to propagate to the output in a gate. Okay, so the gate delay is the time it takes for the output of the gate to respond to a change in the input. Yeah.
Would that include if you had like an OR gate that had several different inputs, and like say there was 5 inputs and 4 of them were already there, the 5th input signal hadn't gotten to it yet? Would that count as gate delay or something else?
The gate delay, so the question is, suppose you have a 4-input gate, 3 inputs are staying the same, and the 4th one changes. It's the time it takes that, there will be a time delay between when that 4th one changes and the output changes as a result of that change. I don't know if that answered your question or not.
What I mean is, like, if the 4th gate is caught up earlier on in the bus? Like,
Oh, we are going to examine that problem in a lot of detail later on.
okay.
Because what happens is you have all these gates and they're all cascaded together, and it's, you know, it's kind of like the weakest link in the chain. It's the longest gate delay from the beginning of the combinational circuit to the output of that circuit is the one that you have to design for. Do you see how that works? It's kind of like in business, your business, right? Don't they have? Isn't there a bottleneck? Yeah. And is there a chart called a PERT chart?
I don't remember.
Well, anyway, you know, for if you have a construction job, where do you put your resources? You put your resources in the bottleneck, and one of the bottlenecks is the longest in a circuit is the longest number of gates between input and output. But what we have seen here is that every combinational circuit, no matter what, has a truth table. And from that truth table, we can write it as an and of or. Are you with me? Mm-hmm. So because any combinational circuit can be transformed into an and or circuit, actually you can also do an or and. You know? Mm-hmm. That means that any combinational function can be computed with 2 gate delays.
It's cool.
That's the time-space problem then.
It is because it might be prohibitively expensive in space to do it that way, and frequently that in fact is the case. It's frequently prohibitive to do it, to have everything as an and, as a 2-level and or. Yeah. Now there's a statement here that says as an and or circuit or as an or and circuit. It's actually possible to do an or and I need to show you, we need to see how to do that. Because this and, so what was our and or? It had a whole bunch of and gates and they were going into one what? Or gate. But on the other hand, by duality, you could have a whole bunch of what? Or gates and go into one and gate. Do you see what I'm saying? And it's actually possible to do it both ways. All right. Okay. Well, anyway, this is a two-level and or network, and this is an and of ors. Now, here's the thing. It's also possible to have an or of ands. Okay. So now an or and two-level network. I'll show you how to make the or and. It's possible to have an or and network, in which case we have what? Does everybody see that we have A or B prime or C prime and A prime or B prime or C. So here what you would do is you'd have A, B prime, C prime going into the first level OR gate, A prime, B prime, C going into the next, to another first level OR gate, and then those feed into the AND. Okay? So it's possible to have AND of ORs, and it's also possible to have OR of ANDs. And we need to be able to go back and forth between each one. Okay? So here's the recipe. And or, oh, by the way, here's what we're going to do. This is, the way we're going to, instead of saying, this gets confusing. This is a what? A what of what?
An or of and.
This is an or of ands. But here's how we're going to refer to it from now on. We're going to call this an and or circuit.
It's the opposite.
Yeah, but I think that's easier. Okay? And this one in figure 10.20 is going to be an or and circuit. Are you with me? So we have and or circuits and or and circuits. Okay? And so here is and or versus or and. And let me say why we're going to do it this way. It's because Boolean algebra is corresponds to addition and multiplication because and corresponds to multiplication and or corresponds to addition, it's easier to do algebra. We are used to doing algebra to get rid of parentheses and to get like A, B, C plus D, E, F plus, A. You see what I mean? It's easier for us to do our algebraic manipulations to produce and or circuits. It's very difficult. I've tried it. Well, you should be able to, because of this duality, but it's really hard to break the habit and to try to get something like using Boolean algebra to get it to an or and circuit. You see what I mean? So basically what we do is to transform any expression x to an equivalent or and, it's easier to transform the complement of x to an and or expression without parentheses, the same way that we've just been doing it, and then use x equals x prime prime and De Morgan's law to get it into an or and circuit. All right? Now here, and I think what we should do, let's do an example. Let me just make one up. Let's suppose that we have this. Let's suppose that we have so write the following expression as an or and circuit. Okay? That's going to be our problem. And here let's just have this. Let's say x. Okay, let's suppose that we have this expression. X equals A prime B C or B prime. All right? This is about take 3. Okay, now the first thing we have to do is it says transform the complement of x to an and or expression. So what is the complement of x? X prime is what? It's A prime B C or B prime prime, right? Is everybody with me on this? Okay, but this equals, so now we have to do De Morgan's on this. So how do we do De Morgan's on this? This is what? Quantity A prime B C prime what? Prime and what? And B prime and, yeah, B prime prime.
The C doesn't have a prime.
Oh, sorry. Is everybody clear on that? Okay, but what is this? Now we do De Morgan on this, and what is this? This is A prime prime. Can we do double negation in our head?
Yes.
So this is A prime or what? B prime or C prime, right? And what? B. So now we use distributive law, and what do we get? AB or what? B prime B or what?
C prime B.
Yeah, but we do it in
Or
alphabetic
B, C
order. B, C prime. But what is B prime B?
0.
0. So this is AB or 0 or B, C prime. But what is 0 or anything?
Itself.
So this is AB
Or B, C prime.
or BC prime. Is everybody with me on this? Now watch this. So now x prime, we know that x prime is this. So what is x? So what is x? So x is x prime prime. So that's this prime. Are you with me? So it is AB or BC prime prime. Is everybody, are we good? But De Morgan on this is what? A, now let's do two, can we do two steps at once?
Sure.
Because this is going to be, oh no, we'll do it. Okay, we'll do AB, this is AB prime or what? BC prime, oh sorry, and BC prime prime. But De Morgan again is what? A prime or B prime and what? B prime or C. And voila.
Oh. Or and.
Yeah.
Oh.
How do you say that? Well, how do you say that? How do you spell that in French?
L-A.
Voila. Yeah, voila. This is an or and circuit, right? Does everybody see how that works? So what you do is, whatever expression you do, you calculate the complement of that, and you get it into an and or expression, and then you use double negation on this to get it to this. And I think there's going to be a homework problem where you need to do that. And now here's another. Let me just do one more thing. Here's another thing that's interesting is that if we go back and look at this table, look at figure 10.17. Let's do one more thing. Figure 10.7, the table on figure 10.17. Check it out. Do you remember when we did the and or circuit for this? We had a whole bunch. How many and terms did we have? We had 6. But look, how would we write this as an or and circuit?
There'd be 2.
There would only be 2. We look at where there's a what?
0.
We look at where there's the zeros. Are you with me? We look at where there's a 0, and what do we do? So let's do figure 1017. And now, let me see. So it's going to be, when A is, so now when is it 0? We have to make, now we don't say when it's 1, we have to say when it's 0. So now, do you see that this is going to be, if A is, it would be A or, so what would this, so X would equal what? A what? Or B prime or C prime. Now here's the thing. This is always going to be 1, except for one place where it's going to be 0, right? Because if A is 0 and B is 1 and C is 1, this will be 0 or 0 or 0. Yeah? And what?
A or B or C prime.
Yeah, A or B or C prime.
I got that.
B.
I think
Oh, is it the opposite?
A
A.
prime or
Yeah, and if you can always figure out what you want, what you or C. And you can always figure it out because what you want is you want this whole thing to be 0 for precisely this combination. Yeah? Is everybody with me on this? Good deal. Sorry I kept you a little late. See you tomorrow for the lab. Now we do De Morgan on the whole thing, right? Oh, I picked one that's way too complicated. I'll tell you what let's do. No, I'll tell you what let's do. Let's change the problem. Let's get rid of this prime. Are you with me? Let's get rid of this prime. This is it, yeah. Okay, hold on. Now we've just done the first part of this. All right. So yeah, I was way ambitious by putting that outer prime. Okay, is everybody clear that now we have this as this is an and or circuit, yeah? Now what you do is we say, so this is, oh,
But now we have to do De Morgan's anyway. So.
yeah, now we have to do De Morgan's anyway.
That's okay.
And we can then use it.
That's what I get for making up these things in the, you know, on the fly.
Let's push it back.
I tell you what, I'm gonna cut all that stuff out of the video, and let's see. Okay, so what we're gonna do is let's write the following. Okay, fortunately this is not gonna be.